So last time we talked about the basic algebraic operation for limit of sequences. We talked about the monotone convergence theorem. So the monotone convergence theorem was that you had a sequence that was increasing, or it could be decreasing. So either it was increasing. This meant that the next element was bigger or equal to the previous, and then they were all assumed to be bounded. If you had such a sequence, or similarly, if you had a sequence, so this was the increasing case, then there was a similar decreasing case where the previous is bigger or equal to the next one. And then they are assumed to be bounded from below. So this was decreasing. So monotone convergence theorem was that if you had a bounded increasing sequence or a bounded decreasing sequence, in either case, the sequence is convergent, and it's converging in the first case, in this case here, A. It's converged to the sup of the xn, to the in case A. And in the case B, it converts to the inf. In case B. Right. So that was the monotone convergence theorem. And the third thing we talk about, and that's where we will continue today, is Cauchy sequence. So we talked about Cauchy sequence. So let me, and we put a few things about Cauchy sequence, but we want to examine that more today. So let me remind you what a Cauchy sequence is. So a sequence xn is said to be a Cauchy sequence if for all epsilon greater than 0, there exists n such that if little n is bigger or equal to the capital N, then, if little n and little m, so if n and m and n are bigger or equal, then they are epsilon close together, xn and xm, the distance between them is at least epsilon. So this was a Cauchy sequence, and it just meant, Cauchy sequence just meant that the tail, right, of the sequence bunch together. Right. Now, let me just prove. I think we maybe talk about this, but I'm going to let me just use a little theorem here. If xn is a Cauchy sequence, then xn is bounded. And so the proof of this is the proof. So now in the definition of it being a Cauchy sequence, you can take epsilon to be equal to 1. So if you take epsilon to be equal to 1, in the definition of being a Cauchy sequence, so this means that there exists some n such that if little n and little m are bigger than this n, then the difference between these two is less than 1. Right? This is the definition where I just apply it to epsilon equal to 1. Right? So you have this. But of course, in particular, we can set, say, m equal to this. Right? And then you have that xn, all the other ones. This means that for all, then for all little n bigger than capital N, if you're looking at this difference here, then this is less than 1. I'm only applying this now. I just choose just one single m, and I'm choosing it to be equal to that capital. So you have that. And so this means that now you see that if you take now, so if you take x, so now suppose that little n, so for little n bigger than capital N, if you look at such a little n, then you have so for little n bigger or equal to capital N, then you have that the norm of little n, well, you can write little n as the difference. You can write little n, right? You can subtract it first and then add it again. So this is clearly the same. And now you can just, so you have the sum of two things. You can think about this thing here as one number, and this is another number. So this is now less than xn minus x capital N plus the norm of x capital N. And this here was, because little n was bigger than capital N, this here is bounded by 1. So this is less than 1 plus the norm. This. So you see that for all the little n's that are bigger than capital N, all of those, there is a uniform bound, right? And so this means that if you're now just taking the maximum of the norm of x1, the norm of x2, up to the norm of xn xn minus 1, and then x capital N plus 1. If you take the maximum of this and call this n, then clearly for all n, clearly you have for all n, you have that xn is less or equal to n. Right? Because if n, little n is bigger than capital N, then it's bounded by capital M because it's a maximum in particular of this, and all the other ones, that's sort of obvious. Okay, so it means that if you have a Cauchy sequence, it's automatically bounded. Okay. Now we have the Cauchy Convergence Theorem. So next we will discuss is the Cauchy Convergence Theorem. So this is the following: that any Cauchy sequence is convergent. Okay. So remember that last time we proved the following theorem. So recall that last time we showed the converse. So namely, we proved the following theorem. We proved that if that any convergent sequence is a Cauchy sequence. And so the Cauchy convergence theorem is a converse to this. Now, so we'll come back to the proof in just a little bit. But before that, let me talk about some applications. And so the first one, we sort of started talking a little bit last time, and this is the contracting mapping theorem. So contracting, and that in itself have a number of applications. So contracting mapping theorem. And for that, I need to recall some definitions. So, a map T from R into R is said to be a contracting map if there exists some constant C positive, C is positive, and the key point is it will have to be positive. So but the key point is that this constant has to be strictly less than 1. And then contracting mapping just means that if you're looking at the difference between the images, then they are closer together. They're strictly closer together than the points that they are images of. Okay, so this is a contracting mapping. Right, and so the contracting mapping, again, this here inequality is, it's saying that under the map, the images are squeezed more together. So now, that's one concept. The other one we need is that for fixed point. The other concept is fixed point. So X here is a fixed point for a map T if under the map the points remain unchanged. So T of X is equal to X. So this is what it needs to be a fixed point. Yeah.
But that, it's not the same C for X and Y.
It is the same C.
It is.
Yeah, it's the same C. Yeah. And we'll come back to this in just a second. But it is supposed to be the same C. You can weaken that a little bit, but essentially, I mean, you sort of, at least, we'll talk about this in just a second. But it's important. Just think about it, that it's a requirement that it's the same C for all. And the key point is that this C is strictly less than 1. Okay, so this is a fixed point. Okay. And now, so now the first little lemma is that. So we have a lemma here. If T here is a contracting map, then then there's at most one fixed point. There cannot be more than one fixed point. Okay? So let's prove that. It's a proof. So I'm going to suppose x and y are fixed points. And I want to show that x is equal to y. Right? So I'm looking at the images. So let's continue. So I'm looking at the images under F. So I'm looking at, so I take T of X, and I'm looking at the difference between T of X and T of Y. And I want to estimate that difference. Well, on one hand, X is supposed to be a fixed point. So T of X is the same as X. And likewise for Y. So this here is the same. So T of X is the same as X. T of Y is supposed to be the same as Y. So I have this. On the other hand, it's a contracting map. So this here is less or equal to C times the norm of X minus Y. But now C here, remember C is strictly less than 1. So you can only have an inequality like this, right, if this number here is 0, right, when C is strictly less than 1. So this here implies that X minus Y, the distance is 0, and so of course this means that X is equal to Y. Okay, so that's what we want to prove. Yeah.
The definition of the contracting map
Yeah.
also less than or equal to.
Yeah, I'm sorry. That was, yeah, it should have been less equal to. Because otherwise, you know, it wouldn't be, if X is equal to Y, it wouldn't be that. So it should be less equal to. Okay, so a contracting map have at most one fixed point. Okay, now let's so let me just, so you're going to do this. So I have harassed the graders to give you back the homework. It should be back today. I mean, otherwise they're in trouble. So hopefully, and the assignment for next week is already posted. And here's so this is on the next. So I will. So here's something on PZ3, and I think it's okay. Yeah, I forget which one it is, but anyway, on the third PZ, you will be asked to prove the following: that if T here is a contracting map, and X here is any point in the domain of this map, then if you form the sequence AN, so A1, say, that's just X, A2, let's call it A, sorry, let's call it A0 is X, A1 here is T of X, T of A0, so this is T of X, and A2 is T of A1, So this is the same as t of this, so this is t times t of x, which I will write like this. And A3, so we continue this way, A3 is t of A2, so that is t applied 3 times, so t of x, and I'm going to write this as t cube of x, and so on. So an is going to be t of it's t an plus 1 is going to be t of an. So that's the same as t to the power n plus 1 of x. Okay. So if you have a contracting map and you just start with any point you want, and now you form a sequence that is based on that point, and the nth element is just where you have applied the map n times to the original point. So if you form that sequence, then you will prove, you will show that in the homework, you will show that this sequence, so p set 3, and I will just do a special case of it that you will start with, but we'll just do this now. And then the rest I leave for the homework. But on p set 3, you prove that this an is a Cauchy sequence. And what is the key starting point? So key starting point for this. So now, because you're here, you're already well started on p set 3. Because the key starting point for this is to prove that it's a Cauchy sequence. So I want to estimate. So this is not enough, right? I mean, I need to prove. What I need to show is, right, remember, I need to prove that when little m and little n are sufficiently large, then I want to estimate the distance between these two and show that they're bunched together, right? That's what we need to prove it's Cauchy sequence. I won't quite do this, but I'll do a special case that is the key starting point. And that is the way I'm looking at this thing here. I'm looking at 2 consecutive elements in the sequence, and I'm estimating the distance. Right? That's not enough to prove that it's a Cauchy sequence, right? Because I need to prove that for all n and m sufficiently large. And I'm just proving here that for any n sufficiently large, if I'm looking at the neighbor, then the distance is very small. But you can use the estimates that we will now prove to prove that it is, in fact, a Cauchy sequence. So in order to estimate this, right, I can think about this thing here as t as a to the n plus 1. This here is just t of a to the n, and an itself, this is t of the previous element, right? This is how we define them. So this means that this thing here, so again, I can just write this in here. So this thing is equal to an minus t of an minus 1. And now I can use that as a contracting map, right? Because now I have these 2 t's here. So I can use that as a contracting map, so I get less or equal to, and then an minus 1. And so you see that the distance between the next pair is, because c is strictly less than 1, it has decreased with some factor, right? And so now the key starting point is that if you just iterate this, So now if I iterate this, so I'm looking at an plus 1 minus an, and I now have that this thing here is less than c an minus 1. But now I'm writing, forget about the c for a second. I'm just writing this thing here, so I do the same thing again. I write this here as the image of an minus 1, and I write this n minus 1 as the image of the previous one, so n minus 2, right? And now, so I write this, so c here, I just have to carry along for the right, and then I have t an minus 1 minus t an minus 2. And now forget about this, just use this contracting mapping. So then this is less than equal to, and then the c I have to carry along. But then there's another c that pops out, right? So this times c that pops out because of the contracting mapping, and then an minus 1 minus an minus 2. And so you see that you have written this as c squared an minus 2 minus 1 minus an minus 2. And so now you continue it. And so you see that the further out you get, right, so you continue this all the way down to that you're getting that this element is the initial point, and this one is the first element, A1. This is A0, and this is A1, right? And so you see that you're getting something which is like a c to some power n times the distance that you started with, right? So this is bounded by something like c to the n times a, the 1 minus a0, something like that. And so that's a key starting point. So if you're going very, very far out, remember that this number is smaller than 1. So this here will become incredibly small when n is large, right? And so this is the key starting point to prove that if you take a contracting map, you start with any point, and you form this sequence here, then it's a Cauchy sequence. So now, and I leave the rest for the homework. Now let's prove the contracting mapping theorem using the Cauchy Convergence Theorem. So using the Cauchy Convergence Theorem, will now prove the contracting mapping theorem. Okay, so what is the contracting mapping theorem? The contracting mapping theorem is that if T here is a contracting map, so T from R to R, maps R into R, gives a contracting map. Then T has a fixed point. We already know that such a fixed point is unique. Right? We already proved that there can at most be one fixed point. Okay, so let's try to prove that. So we're going to use this result from PCF3. To prove. So I start with any point x. You pick any point you want, and then we form the sequence where you apply this here n time to x. Now we have that, so then we have, so this is this p set from p set 3, that an is a Cauchy sequence. Okay, but then from Cauchy's convergence theorem, we have that an is converging, right? That this here is a Cauchy sequence, but the Cauchy convergence theorem say that any Cauchy sequence is actually convergent. So this here converges to some a. Okay. And now the idea is that we want to show. So want to show that a is a fixed point. So that's the idea. This is a kind of the contracting mapping theorem is actually extremely powerful. It can be used to solve what's called ODE, ordinary differential equations. And we'll talk a little bit about that at some later point in the class. But it can also be used to solve PDEs, which is more complicated, partial differential equation, and in all kind of other areas of math. Okay, so now we want to prove that this A here is a fixed point. And so we have, and we'll come back in just a minute. We'll prove something related to this, but let me just very simple. So I'm talking about an here. I know that it's converting to a. I then look at the sequence T of an. Well, T of an, that was an plus 1. Right, it was just one further out of the sequence, right? But so since an converge, this means, of course, that since an converges to a, this means that these here will also converge to a. So since this here, an plus 1 as n become very large, it will converge to a. Okay. Now, if you're looking at T of an, so you want to estimate now. So what I want to prove is, right, so now I'm looking at this distance. So I want to show, we want to show that T of a, right, is equal to a. That's what we want to prove. And so if I'm looking at T of an, right, T of an, this here was an plus 1. And so if I'm looking at T of an plus an minus T of a, right, because it is a contracting map, this thing here is bounded, is less or equal to C an minus a. Right? And this is also equal to an plus 1 minus T of a. That was just the definition of the an plus 1. So now I have that an converts to a. So this means that this here converts to 0, right? So now since an converts to a, then you have that an minus a. You can think about this as a sequence that converges to 0. But this inequality here, say that since this here goes to 0, this thing here must also go to 0. So you see that, therefore, an plus 1 minus t of a goes to 0. Right? So, but that this here goes to 0, this just means that an plus 1, this must converge to t of a. Right? But this sequence already converts to a. There can only be one limit. Right? So we already have that an plus 1 converts to a. But then these two numbers must be the same. Right? So the conclusion here is that a must be equal to t of a. Okay? So from the Cauchy Convergence Theorem, then you get the contracting mapping theorem, and we already proved that there was, you get a fixed point, and we already knew that there was at most one fixed point. And so this is a very powerful idea, because for many things, it's almost impossible to find the actual fixed point. But what you do is that you're starting with some, right? So in this case, you just said you pick any x, and then you just apply the map enough times, right? Sometimes you would start with you can't find a fixed point, but you can find something pretty close to the fixed point. And then you iterate from there on. And we'll see just in a second. So I already talked about that this applies to the existence of solutions to ODEs and to PDEs. And now let me illustrate this last point in another example. And this comes back to your question about, is this the same? But do think about it as being the same for all x and y. But you could have some kind of local statement where it was true for x and y in some small range, and that would be enough to guarantee you a fixed point. But in general, you should just, it's the same in the definition. It's supposed to be the same for all x and y. But so let me explain that in what's called Newton method. So this is Newton method. And so the idea is that you have a function. You have some function here. F, maybe it doesn't look like a function, but it's supposed to. This is f of x. And you want to find where this, or you want to find the point where this function vanishes. Okay? And so the method is sort of a numerical method to find such a point. If this function was very simple, like a linear function or quadratic function, then of course it would be easy to find. But maybe this is a very complicated function. And so you wouldn't necessarily be able to say exactly what the point is. And so the idea is then, so Newton's methods require that you start with a good guess. But this is the idea of the Newton method. So here's the idea. That we're looking at a function like this. I'm going to assume that this is that is not zero. So it's actually monotone is either increasing or decreasing. So I'm assuming that there's nowhere where the differential vanishes. And then I defined a map T of x to be equal to x minus f of x, f prime of x. This seems kind of, well, it seems, yeah, it seems maybe far away from contracting now. But if you define it like this, now let me take the derivative of this. If I take the derivative of this map, then I get that this in here, the derivative of x, that's just 1. The derivative of this in here, this is a quotient, so it's f prime times, right, it's the derivative of this times f prime, and then f prime squared minus, and then f double prime, right, like that. Right, that's a quotient for taking the derivative. And so you see that you can write this, if you split this up into 2, this here is 1, you split it up to 2, this here is f prime squared divided by f prime squared, and then this here becomes plus, and then I'm writing it as f double prime over f prime squared. And so you see that this in here cancel with that, so these are cancel. So you have that the derivative of this map is just f of x, f prime double prime of x, f prime of x, and then squared. That's the derivative. And now, of course, if I'm using the mean value theorem here, then I have that the derivative then I have that t of x minus t of y. Right, the mean value theorem saying that this thing here is the derivative. It's actually like Waller theorem or whatever, but you can also think about this mean value theorem. It's the derivative at somewhere in between x and y times the difference between x and y. Right? That's the mean value theorem. So you see that if we already knew, so if we can show, if we knew that the derivative was bounded everywhere, was bounded by some c, little c that was less than 1. Right? If you had that, then of course, then you just take absolute value of this. So then you have the t of x minus t of y. The absolute value was equal to t prime in this intermediate point, x minus y. But in this intermediate point, we're assuming that everywhere the derivative is less or equal to c. So this here is now, this is less or equal to c. So c x minus y. And we're assuming that c is strictly less than 1. So you see that this here, if we knew that the derivative of t was strictly less than 1 everywhere, then we would know that this map is a contracting map. Okay, but of course, you know, what we have for the derivative is we have this in here. And so now, but now the idea is that if you start with a really good guess, so if you start with a, so the idea is, the idea of the Newton method is start with a good guess. Good guess. I mean, I'm not going to make that too precise, so I'm putting in quotation marks, but the idea is that you want to, so good guesses, remember that what we want is, we want to find a point. We're interested in this point here, where this function here, we're interested in a point where the function vanishes, right? So starting with a good guess means that you may not start where the function vanishes, but you're starting somewhere where the value is really small, right? That would be a good guess, right? And so, so start with a good guess, meaning that f at that point is small, is very small. Now, of course, you're going to ask, what do you mean by very small? So very small here is going to mean that the value, so now we have, right, from this here, so we have that the derivative here of this map here was equal to these two terms cancel out. So this is f of x, f double prime of x, f prime of x squared. So starting with a good guess means that this thing here is really, really small. And in fact, I want it to be small compared with this, right? So if this here is really small compared with that, then I can guarantee that the absolute value of this is smaller than 1, right? And so you see that if you start with a really good guess, then it would be a contracting mapping, right? And then, of course, you need to prove that, so you're forming the sequence, right? And you need to prove, somehow you need to estimate that you need to be able to say that once you form the sequence, you know, the next thing that is spitting out is also a good guess, right? So that you stay in this range of good guess, right? And if it has this property, then it would be a contracting map, and you would guarantee to get a fixed point, right? But that's all the Newton methods say, right? So you need to kind of justify why, if you start with a good guess, why you keep, as you're iterating this process, why you keep in the range of good guesses. But you know, the Newton method doesn't tell you anything about that, but it requires that to be applied. And so, okay, so it's a contracting map. This T is a contracting map, right? If I can start with a good guess, and when I do this, when I form, so I start with this good guess, and then I'm looking at that the next thing is this T of x, and then I T squared of x, right? And I want all of these to also be good guesses. And then I'm saying that as n goes to infinity, these here is going to converge to this fixed point. I guess I called it x0. Well, this is the fixed point. Fixed point for t. Now, so now we started with a function, and what we were interested in, we wanted to find a root, so a x0 where this function vanishes, right? And I constructed a contracting map, but now I will need to relate this contracting map, or the fixed point for the contracting map, to the original problem. So what is a fixed point for the contracting map? So the map here, the map we defined was t of x is equal to x minus f of x over f prime of x. But a fixed point, so if x0 is a fixed point, then this means that this here is the same as x0 minus f of x0, f prime of x0. And now you can just, right, so therefore this implies that f of x0 minus f of x0 over f prime of x0, this here, you can subtract x0 on both sides, that this is equal to 0. But that, of course, means that the denominator must be 0. So a fixed point is indeed a point where f of x0 is equal to 0. Okay. Now, So now we want to prove the Cauchy Convergence Theorem. But we're going to cheat just a little bit because we are going to deduce it from another theorem that I will prove next time. So to prove the Cauchy Convergence Theorem, I need the Bolzano-Weierstrass theorem, and that theorem we'll prove next time. So what is the Bolzano? So the Bolzano-Weierstrass theorem. So the Bolzano-Weierstrass theorem says that every bounded sequence has a convergent subsequence. So that's a Bolzano-Weierstrass theorem. Okay. Now let's try to assume this again. I'll prove this next time. So let's use this here to prove the Cauchy convergence theorem. So from the Bolzano-Weierstrass theorem, we get the Cauchy convergence theorem. As follows. So remember the Cauchy convergence theorem saying that if you have a Cauchy sequence, then it is convergent. So suppose Xn is a Cauchy sequence. Okay? I want to prove that it's convergent. But we already showed that any Cauchy sequence, shown that Xn, any Cauchy sequence is bounded. Right? This we proved earlier. So now therefore by the Bolzano-Weierstrass theorem, there's a subsequence, a convergent subsequence. So there's a convergent subsequence, Xnk. So now, so you have that this subsequence here converge to some x. And now I want to show that the original sequence converges to x. So since Xn is a Cauchy sequence, given epsilon greater than 0, there there exists capital N, so that if M and N are bigger than capital N, then xn minus xm is less than epsilon over 2, using the epsilon over 2 in the definition of being a Cauchy sequence. But now let's call this the existor n, let's call it n1. So now since x and k converge to x, there exists for that epsilon, there exists n2, k2, n2, yeah. So that if k here is bigger than n2, then xnk minus x is less than epsilon over 2. Okay. So now you just take. So now we take n to be equal to the maximum of n1 and n2. This is the one that corresponds to, right? So this is where k is taken equal to this n2. So if we take n like that, and you're looking at n bigger or equal to n, and you now want to estimate this thing here, then you can think about this difference here as x minus x n2 plus, xn, like this, minus plus xn minus x n over x times like that. And this here is now in this, so this is now in this subsequence. And so one of them, this is less than epsilon over 2, and this here is less than epsilon over 2. And so you get that this difference here was less than epsilon. Okay. Now, so this is why the Bolzano-Weierstrass theorem implies the Cauchy convergence theorem. Okay, so now the next thing is that I want to give another application of the Cauchy convergence theorem. So here's another application of the Cauchy convergence theorem. Right, so one application was to the contracting mapping theorem, but here's another application of the Cauchy convergence theorem. So this is the extreme value theorem. Now, before I explain that, let me introduce this notion of a function being continuous in a rigorous way. So what does it mean for a function to be continuous? So a function f, say from R to R, could be a subset of R, it could be all of R, is said to be continuous at x0, at some point x0, if for all epsilon greater than 0, there exists delta greater than 0, such that if x minus x0 is smaller than delta, then the images are within epsilon of each other. So if you think about it, so if you have like the function, this is a function, you to say that it's continuous at some x0 means that if this thing here is, this here is now f of x0, if you take a little interval around here, this is an epsilon interval around here, then there should be some delta interval around here, so that if you're looking at images here, then it will map into here. Right, that's what it means to be continuous. Okay, so this is continuous at a point, and a function is said to be continuous if it's continuous at all points. So a function is said to be continuous if it is continuous at all points. And so now we have a little theorem here, and this is often useful way of thinking about continuity. So if f is continuous, so let's say f, let's just say it doesn't need to be all of R, but you just have to be careful that everything that you talk about is in the domain, but let's just say that f is a function from R to R, is continuous. So if f is continuous and xn is a sequence that converges to x, then the images, so f of xn, this is another sequence, those converge to f of x. This is a useful way of thinking about it, being continuous. And so now why is this the case? So since f is continuous, you only need that it's continuous at this x. So since it's continuous at x, this means that for all epsilon, or given epsilon greater than 0, there exists delta greater than 0, such that if x minus y, this is this x here that you think about is fixed. If you have another point that is within delta, then the images f of x minus f of y. This is just that it's continuous at that one point x. Okay. Now, since xn converges to x, right? Since xn converges to x, this means that if you use this delta here in the definition of convergence, then there exists capital N such that if little n is bigger than capital N, then xn minus x is less than delta. But now you see that if little n is bigger than capital N, then this lies this close to x, but then this say that the images, so therefore the images f of xn minus f of x is less than epsilon. And this was just as long as little n was bigger than capital N. That's exactly proving that this sequence converts to that. Right? So that's the claim. Okay. Now let's prove the extreme value theorem. So I need to state that first. And there's two versions of it. So extreme value theorem. So you take a function f on some interval, a and b a real number. They're both included. And f here is continuous. It's continuous at all points. It needs to be continuous at all points. And this interval needs to contain the endpoint total. So if this here is continuous, then the sup of f is achieved. At some x. So meaning that sup of f over this interval is equal to the value, let's call it x capital M, capital M for max. It's achieved at some point. Right? In particular, the sup is finite. Right? The sup is finite, and it's not really a sup, it's a max. Right? And so likewise, it also says that, moreover, just the same thing, and you could, in the usual way, you could obtain it from this by looking at the function minus f if you wanted, or you could just prove it directly with the same proof that we're going to give here. Moreover, the inf of f over this interval is equal to the value at some point. So it's not, it's not just an inf, it actually is a minimum where x little m is. And so now let's try to prove that. And so this is going to use this theorem that we proved this theorem, and then it's going to use the Cauchy Convergence Theorem. Okay. So, and I'm just going to prove, like, just because there's two parts to the extreme value theorem. There's this with the sup, and there's this with the inf, but the proof are, with obvious modification, they're the same. Okay, so I'm just going to focus on the sup. So I want to prove, so I'm looking at the soup of this function. A priori, the soup could be infinity. Okay, so usually we like soup to be finite, but let me allow this, that if there is no upper bound, then I will write infinity. So in any case, there exist xn, so that xn, so that f, there exists a sequence in this domain here, so that the f of xn converge to the soup of f. Right. Okay, I'm allowing here, and we don't usually like this, but I allow this here to be infinite. If it's infinite, then I just mean that there's a sequence where the value of these become larger and larger without it. Right. So I have that. But now you see this here is in this range. So this is a bounded, so note that xn, is a bounded sequence. So then I'm using not Cauchy Convergence Theorem, I'm using the Bolzano-Weierstrass theorem, which applies the Cauchy Convergence Theorem. But I will use the Bolzano-Weierstrass theorem, so it's a bounded sequence. So I know that there exists a convergent subsequence. It's a good exercise to see that this sequence in itself, you can just draw a little picture and you convince yourself that this sequence in itself may not be convergent. But after you pass to a subsequence, you can find a convergent subsequence. So it converges. So this here converges, and it converges to something in this interval, right? And that's important. So it converges to some x, and I call this x capital M. Okay. So it's converging, and the key point here is that this thing here is lying in this interval, and the function is defined in particular at this point. Right? So if this here had not included the endpoint, it converts to one of the endpoints, but the function would not be defined there. So you wouldn't be able to conclude the extreme direct limit. But anyway, so since we include the endpoint here, then now we have that from this theorem that is right here. We have that since this sequence converts to that, we have that the images convert to the image of x capital N, right? But on the other hand, this sequence here was a subsequence of a sequence that converts to the soup, right? But if you take a sequence that converts to whatever number, then any subsequence will convert to the same number. So this here also converts to the soup, to soup of F. Right? And so this means that these two numbers here must be the same. Right? And so you should just, it will take you just a second to convince yourself that everything is fine. If a priori I didn't know that the soup was a finite number, but infinite, right? That it's still fine. But that should also take a minute to convince yourself about that. So that proves the extreme value theorem, right? That if you take a function that is continuous and defined on an interval where the interval includes both endpoints, then the soup is achieved. So the soup is really a max, and the int, it's very similar proof. The infimum is also achieved, and so both the min and max exist. Yeah. Sorry.
How do we know that such extent is good?
Okay, so that was the, so yeah, that's right. So you're saying, so this here, so it was clear enough that it was a bounded sequence because it's lying in this bounded interval, right? So it's a bounded sequence. Are you asking why such a bounded sequence exists? Okay, so I just, so you have this function, right? So like this, so you take the sup of f over this interval. And so this means that if you take any epsilon and you subtract it from the sup, right? Then actually there must exist a x depending on this epsilon, there must exist so that the value at this x is larger than this, right? And so you could imagine, instead of epsilon here, looking at a sequence like this, and then this here gives you a sequence like that. And so, right, so that would be how you construct this. And the same when you do this. And so once you have it, it's a bounded sequence because it's lie between A and B, right? You're using the Bolzano-Weierstrass theorem that we'll prove next time to get a convergent subsequence. And then you apply the theorem, this theorem here, right, to get that both, in that case, the maximum, and likewise for the minimum, that they are achieved. Any questions? Great.